Hello everybody, welcome back. Today we're going to take a look at some properties of matrices. We have a lot of definitions here. Um, this first box up here is all different characteristics of certain matrices, whereas this box down here is full of properties that hold for every matrix, or every two matrices, as the case may be. So for part A, we have to show that if A and B are symmetric, then AB is not symmetric unless A and B commute. So we can see here that for part A, we have a matrix A that is symmetric, and we have a matrix B that is symmetric. Um, we can look down here from the definition of transpose that this means that the element ij of A is because it's equal to its own transpose, uh, the ijth element is equal to the jith element for both of these, in fact. Ij is equal to B of ji. Okay, and what we want to show is that uh, here, just to make it clear, this is not what we have proven yet, but we want to show is that if actually if and only if, but that's beside the point. If A B equals B A from the definition of commutative, if A B equals B A, then for these vectors A B element ij is equal to the jith element of AB using the same definitions as before. Okay. Um, so now, let's start off with this here. Um, so AB, the ijth element, by our definition of matrix multiplication down here, is the same as the sum of that and I'm just copying this down. Okay. So since we know that we can interchange the addresses of each of these, we can say that this is the same as since they're symmetric. Um, we can rewrite this as a ki b j k, which we can also then rewrite as just swapping them around, since when you address them, they're just numbers, right? And number multiplication is commutative. Oops, I'm writing down the wrong thing. Even if matrix multiplication isn't, number multiplication is. So rewriting that. So what we have, if we apply the definition again, is we have BA, but what we have is the jith element. So since this is part of the if statement here, we can use this and swap them around, meaning that this equals AB JI, which is exactly what we wanted to show. But we wouldn't have been able to do that swap if that part of the if statement wasn't there. So yeah, they are not symmetric unless A and B commute, because commuting them is the only way to get them to be symmetric. And then for part B here, we need to show that the product of orthogonal matrices is orthogonal. So an orthogonal matrix is where its inverse is the same as its transpose. So that means we have two matrices, A and B. I'll draw a little line here. Should have done that before I started writing down the next problem. That's a transpose. So if we want to show that there are that the product is orthogonal, we have to show that a AB inverse is equal to AB transpose. Okay, so let's start off with this and see if we can make it to the other side of the equality. So AB inverse, what can we do with this? Well, we can do this here, the second row in the second box. So that means that the inverse of the product is the product of the inverses in the opposite order. And since we know that A inverse is A transpose and B inverse is B transpose, we can rewrite that as B transpose times A transpose. And then using this, the first formula in this box, we can further rewrite that to be AB transposed, which is exactly what we wanted to show. So the product of orthogonal matrices or the product is orthogonal. For part C, we want to show that if A and B are Hermitian, then AB, the product, is not Hermitian unless A and B commute. So this is similar to part A, but with a couple more tricks in there. Keep in mind the bar on top of that means complex conjugate, as does these bars here. So yeah, so we have, I'll section this off first. We have a matrix A where A equals its complex conjugate's transpose. It will make it very clear that's a T. These symbols here are little daggers, not T's, but it's very hard to draw them. So, and then B, similarly, is equal to the conjugate's transpose of itself. And we want to show that if AB equals BA, then let's see, where is that? Yeah, okay. Then AB equals AB complex conjugate transposed. Okay, so we're going to start this a similar way to part A there. We're going to say that the way you multiply these together is by using this formula here. AIK BKJ. And since the complex conjugate of a matrix is the complex conjugate of each one of the cells, or each one of the elements, we should say, we can rewrite this as, and then also using the definition of transpose that we had up here. Not only are they equal to, well, actually, they are equal to that. We swap the indices and do the complex conjugate of them. Okay. So once again, we can rewrite that to put them in the other order, because once again, we are just multiplying numbers together inside the sum here. And regular numbers do commute. Anyway, so now that we are here, we can rewrite this as, using this formula again, as complex conjugate of B, complex conjugate of A, the jth, ith element. Which, using this formula, we can have the bar extend across the top, since multiplying complex conjugates together is the same as taking the complex conjugate afterwards. Once again, this is only equal to this if AB equals BA. That's the only way that we can swap those around in there and have it still work. But with that being said, we did just show that this is the case if they do commute. And then finally, for part D, show that a product of unitary matrices is unitary. So that means we have a matrix A, where its inverse is equal to its complex conjugate's transpose. And same for B. Okay. So, and yes, yeah. We want to show that AB inverse is equal to AB complex conjugate transpose. So we'll start, once again, we'll start out on one side of the equal sign and make our way to the other. AB inverse, using this formula here, we can rewrite that as B inverse times A inverse. And since we have these formulas here, we can go ahead and substitute those in. B complex conjugate transpose equals A complex conjugate transpose. Furthermore, we can write that by this formula, we can rewrite that as A complex conjugate times B complex conjugate transpose. Finally, by this middle formula here, we can extend the bar across both of them. And this is what we wanted to prove. A lot of work, a lot of technical things, but these sort of relations are important. Thank you for watching.